Hi everybody, this is lesson 3.2, the title of the lesson, Breaking Down the Possibilities. Let's go ahead and read the specific objectives. Students will understand that a sample space can be broken up according to disjoint events and or events that are not disjoint. Some events are not disjoint. They exist a simple law that determines the probability of events involving or. Students will be able to break down a sample space according to conjoined or disjoint events, calculate probability involving or. So this is the lesson where we continue study the probability that was defined in lesson 3.1 that talked about the chance. And now talking about not just one event, but a series of events connected with this, what we call a connective, an or. What is an or, and what does it mean for the events to be disjoint or conjoint? What are those terms? So we'll discover this in this lesson. We'll begin with the following question. A survey is given to collect market research about the demand for product A. The main customer demographic for that product, as it designed, is considered to be woman and Democratic voter. Looking at the question number one, given that approximately half of all American adults are Democrats and approximately half of all American adults are women, what are the chances that a randomly polled adult will qualify as being in the customer demographic? All right, so before I'm going to give you an idea to try to answer that question, one thing that you can think of is to take the United States, and let's describe it with, let's say, a circle, and try to divide this circle in the groups that are listed right here. Okay, so if you look at the gender and you look at the political affiliation, Democrat or Republican, and if we assume that everything is half-half, which is not exactly the case, but just for the purposes of illustration, can you take this circle and separate in a region where you will designate each region either being Democrat or not, or whether being woman or not on that circle? So one way you can think about this is to basically say, okay, what are the possibilities? Well, you can go ahead and divide this into two first and say, okay, one half is going to be the Democrats and the other one are going to be the Republican, let's say. All right, so it's a half-half partition. Okay, and at the same time, you can also separate this in the other two categories, like that, where we can have Democrat woman, Republican woman, and then we can have Democrat men and Republican men. So that breaks our pool of possibilities in 4 regions that are not connected. You see it? So now looking at that, what are the chances that a randomly polled adult will qualify as being in the customer demographic, which is defined as woman and Democrat voters? And also I would like to clarify here. So when we say woman and a Democratic voter, we basically say that the product that we're looking at will be so a person will be interested in that product if they fit either of the category. So it doesn't mean that they have to be a Democratic woman voter, for example. It's basically either or. This is how it was designed. So it's either woman or Democratic voter. So I would say, if we want to write this in terms of probability terms, we'll say what's the probability that we select somebody a person who is either a Democrat or a woman. Okay, so that's what we mean when we, when we have that situation. That's going to be our focus in this lesson, is to look at the possibilities connected with the word or. So it's either that or that is a success. So now, if you understand this question, can you highlight what part of this diagram will fit that case when we select a Democrat or a woman? All right, and then can you write a probability associated with that as a percentage? I'll give you a moment. All right, so now if we review, if we look at this case, whether it is a Democrat or or a woman, then we are going to highlight which region. So it's either woman, including a Republican woman, or it is a Democrat. So we'll also include that region. So the only part of this whole that will not fit the description of a product, if it's a man or it, and at the same time it's a Republican man. Okay, so that's the only one that would not fit that demographics based on this description in this question. So if you look at that case, then that circle has 3 chances for success out of the 4 possibilities. So the answer would be 3/4 or 75%. Moving on, a different product must also be market tested. That product is product B. This product has 3 groups in its target demographic: residents of high-rise buildings, suburban homeowners, and I will also change this to an or, suburban renters. So if you fit in any of these categories, then this is who you're targeting your product to. So these are the people who are going to like this product and buy it or be interested in buying it. All right, so now question is here. If approximately 1% of Americans live in high-rise buildings, 31% of Americans are suburban homeowners, and 6% of Americans live in suburbs or rent in suburbs, what is the probability that a randomly polled American will be in the market demographic of that product? Okay, so once again, the way you want to see this is to visualize as the whole country being a circle, and then we describe these products. So we have 1% are the one that live in high-rise. I'll just abbreviate it as HR, the high-rise. Then we got about 6% that rent. They rent where? In suburbs. And then we got 31%. So we got 1, 6, and we got 31% who live in suburbs. So they homeowners. So own suburbs. And the other ones are whatever, right? The other ones are not included in here. So if we were to randomly select any person from this whole diagram, what is the percentage or likelihood of selecting someone that will fit in either of these 3? What do you think the percent would be? I'll give you a moment. Well, if you look at this diagram, you could see that these groups are not connected whatsoever. All right, unlike before, you can be a woman Democrat, can be a man Democrat, you can be Republican man or woman Republican. So you have 4 different possibilities. Here, these do not overlap. So living in a high-rise and at the same time renting in suburbs doesn't match. They're not connected. So those types of events or those types of categories are called disjoint. They're not connected. While the other ones, the one that we've seen in question 1, they do have, some relationship. They are conjoint. When you have a disjoint events and you just want to calculate the probability, you just simply take those percentages and you just add them together. So you got 31 plus 6 plus 1, and that gives us the probability of 38%. You just add all the groups. Okay, and that happens when you have events that are disjoint. Let's move on to the next question. Okay, a company consisting of 200 employees is trying to recruit for a senior management position. The only people who can apply are current employees of the company. It's also decided that to qualify, applicants must possess either an MBA degree or 5 years of management experience. 86 of the company's employees have an MBA, and it's also known that 40% have at least 5 years of management experience. Part A is asking us, estimate the probability that a randomly selected employee can qualify for the position. So once again, we're going to look at this and make a circle. The circle consists of 200 employees. So that's the total. 100% is 200. All right, so that's the total size of the company. All right, we have 86, which would be a little less than half, right? Half will be 100. So 86 of them have an MBA degree, and thus they qualify to be recruited for that position. And then we also know that 40% have 5 years of management experience. Well, 40% of 200 is what? I'll give you a moment. Well, that's 80, right? So just multiply 40% times 200. So 80 employees. My question to you, are these two disjoint or they conjoint? Do they overlap or they don't overlap based on the information that's provided? What do you think? I'll give you a moment. Let's review. Well, nowhere here it says that the 40% of those who have a 5-year management experience also have an MBA. It does not say so. It just said that 40% have a management experience, but it doesn't tell us what's the overlap. Okay? So whether they overlap, we do not know. So therefore, what do? Well, we can go ahead and look at two possibilities, or maybe let's discuss all the possibilities. So one possibility is that those who have a 5 years experience also have an MBA. So we can say, all 80, all 80 of these, okay, have MBA. All right, so that would mean that, all of these 86 will have MBA, 80 of them also have the management experience, so our circle is just going to be like this. Like this, you see? That's what I'm saying with the overlap. So this is MBA, okay, Master of Business Administration, and then part of that, almost all, will also have the 5-year management degree. So you see, this total right here is going to be the MBA. Okay, and part of this right here is the one that also have 5+ years of management experience. And to calculate the probability, you just simply go ahead and, what's the probability that we select somebody in that region? Probability is defined as a chance, where you take the total number of possibilities, remember, and the numerator is the number of count for your selection or for your success. I like to call it success. So in this case, success will be defined to be put anywhere in this yellow region. So that would be how many? 86. I'll give you a moment to convert that into percent. What would that be? So that's 43%. All right, so that's one possibility. Another possibility is that those who have the 5-year experience do not have an MBA. So in other words, another possibility, it could be that, what is it? The MBAs, those 80 people. Oh, how many? 86, right? So 86, the MBA people, and 80 of those who have 5-year experience, so 5+ years of experience, they don't overlap. So another case is when they completely disjoin. So you have the MBA, and those that have MBA do not have a 5-year experience, and those that have 5-year experience or more are not MBA. So that's another kind of extreme case where they do not completely overlap. Then what's going to happen? Well, then we got 86 MBAs plus 80 of the 5+ years. So you have 166 out of 200 people who can potentially qualify for that promotion, for that position. And 166 divided by 200 is going to be 83%. So basically, the truth of the matter is that the answer could be anywhere between those two numbers, between those two extremes, depending on what is the size of an overlap, which we do not know. We don't know how many have an MBA and a 5-year experience. You see the idea here? That's what we're getting with this lesson. All right? So if these two are completely disjoint events, if this is disjoint, let me move it here so you could see it. If they disjoint, then fine, you just add them up together. But if they conjoin, like in this case, then there's no overlap and the percentage is low. So the truth of the matter is we need more information. And that's where the part B comes in. What other information might be needed in order to make an accurate statement about the probability of a randomly selected employee being qualified for the position? Propose one possibility for this information and use it to calculate the probability described above. So first answer the question on what do we need to know. I'll give you a moment. All right, so what we need to know is how many employees have both MBA and 5+ years of experience. All right, and if we know that information, then we can find that probability. So I'm going to give you that information, and I'll give you a moment to go ahead and calculate the probability of selecting a person who can be recruited or who could apply for that management position. Okay, a senior management position. All right, so I'm providing you that information. Let's say that number is 15. So given 15 have both MBA plus the 5-year experience. So now go ahead and calculate the probability of selecting an employee that can apply for the promotion. So probability, and let's write it using, kind of a language that we're developing right here. Probability of selecting someone who has an MBA or 5+ management experience. All right, so you need to count how many people will fit into that categories. All right, so how many people, and then to get the probability, we got to divide this by 200. Okay, so count how many people have MBA or 5-year management experience. I'll give you a moment to find that number. Okay, then we need to calculate the probability. Okay, so that number is going to be what? You ready to calculate this? So we got, if we visualize this again, check this out. So visually, look at this. You got a circle, again. Out of this circle, we look at 86 that has MBA. Right? Are you following? 86 says MBA. But then we also have 15 of those, 15 of these MBAs that also have what? The 5+ management experience and MBA. And the number of MBAs altogether is 86, so 15 in the management experience. And then what else we got? We got 80, remember 40% who have a 5-year management experience. So 15 already in this group, right? 15 is already in this group. But we have an additional, altogether there are 80. So 80 minus 15 gives us 65. 50, 60. So we need 80, right? So 65 plus 15 is 80. So these are the one that has 5+ management experience. So check this out. You see? Look at this. So there are 86 MBA. All right. There are 80. All right. 80 what? 80 the ones that have the 5-year management experience. So the total number, if you look at this, you see, so 86 includes 15. So it's not actually just 86 here. It's going to be 86 minus 15, which is going to be 71. So altogether, these candidates are going to qualify for promotion. Okay, so this was a little complicated, correct? So we need some kind of an easier way to understand this. And there is, there's a logical way to do this. Check this out. If you want to answer the question on probability, here's what we're going to do. We're going to count how many people have MBA. We're going to count how many people have 5+ years of experience. But when we're adding those together, this 86 and another 80, right? When we're adding them together, we are double counting these 15 people that basically were counted in both twice. So what you're going to do, once you do this, you're going to subtract, minus, and overlap. And this overlap is the fact that they have both the MBA and a 5-year experience. And you're going to take this whole thing and you're going to divide this by the total. So look, numerically it's not too bad. So you take 86, you add 80, and you subtract 15, which is that overlap. And what do we get? Let's use a calculator. This is going to be 151 people out of the total of 200. So 151 out of 200 in this company can qualify and apply for that promotion. So it's 75.5%. So now, let's not get confused and let's basically just wrap it up. Not wrap it up, but write it out in a more concrete ways. So what we just did, when we look at the events that are conjoined, there's some kind of overlap. We have something that's called an addition rule of probability, which is the topic of this lesson. Addition rule of probability. And what that says is that when you are looking at the events that can be connected in any way, like this, probability of A or B, You take probability of the first event, you add the probability of the second event, and you subtract any possible overlap. Okay, so in our case, A and B are the MBAs and having a 5-year management experience. So you add those two together and then you subtract an overlap. And this way, you avoid counting any person or anything in a set more than once. Okay, so let's look at some of these probability involving this or. So this or that happening. Okay, so let's look at the problem situation number 3. So we just were introduced to the probability of A or B event, and this rule can be applied to various situations. So let's look at some classical example. One is a die that we have seen in the previous lesson. We'll look at a regular die. It has 6 faces. Okay, we have numbers from 1 to 6 written on it. Probability of getting any face is going to be 1 out of 6. There are 6 chances of success, 6 different numbers, and one of them is considered to be a lucky one, or the success. Now let's look at this and count the successes. So here it says we roll it once, find probability that you get a number that is either 1 or 4. So probability that you get 1 or a 4. So what would that be? So according to this, you just need to count, okay, how many successes are there? So there's only 1 1 and there's only 1 4. So if you look at this, there are 2 out of 6 chances for success, and if you simplify, you can write it as 1/3, and we're going to keep it as a fraction. Notice here, if you look at an OR probability, okay, having both a 1 and a 4 at the same time is not possible, and therefore the only thing that you're doing right here, if we kind of apply this rule, using a rule, it's a probability that you have a 1, which is 1 out of 6. Probability you have 4, which is also 1 out of 6, minus, and there's no overlap. So this is kind of a longer way to write the same idea, is that there are 2 out of 6 chances for success, which reduces to 1/3. All right, let me give you another one and give you a chance to answer that. It says, what's the probability that number is even or odd? All right, so what would that be? I'll give you a moment to answer it. Well, if we count our probabilities, right, so you got even or odd, well, there are half of the numbers that are even and half of the numbers that are odd. So probability that you have an even number and probability that you have an odd number is going to be the same. Probability that it's an even is 3 out of 6. There are 3 even numbers, 2, 4, 6, and there are 3 odd numbers, 1, 3, 5. And there's no overlap. Even and odd cannot happen simultaneously, so it's 6 out of 6 or 100%. All right, so what's the probability of even or odd? It has to happen, 100%. All right, so part C, the number rolled is 1 or even. 1 or even. Well, if you look at that, again, it's 1 or even. So we're going to go ahead and count this. Probability that it is 1 plus probability that it is even minus probability that it's both 1 and at the same time it's even. Can that happen? Well, probability that it is 1 out of 6. Probability that it's even, it's 3 out of 6. Is it possible for an outcome to be both a 1 and an even number? Well, no, because 1 is not even. So minus 0. So there are 4 out of 6 chances, which is 2/3. For all of these cases, case A, B, and C, these are what we call disjoint events. All right, if you look at this, it's not possible for a number to be 1 and 4 at the same time. It's not possible for a number to be even and odd at the same time. I'm putting 0 over 6. It's not possible. And here it's also 0. It's not possible to be odd or even. So when you have disjoint events, just like we look at the percentages of those suburban renters and all that, you just sum up those probabilities together. You add them together. Part D is different. It says that the number roll is 4 or even. If you think about this, probability that it is a 4 or even, if we write this out, is going to be probability that it is 4 plus probability that it is even minus probability that it is a 4 and an even number at the same time. And in this case, what's the probability that it is a 4? Well, there's one 4 in there. How many of the even numbers of there? Well, there are 2, 4, and 6. There are 3 of them. But there's one number there that it is both 4 and even, which is a 4 itself. It's an even number. So you got to subtract that overlap. So 4 minus 1, it gives you 3 over 6, which gives you back to the 1/2. You might say, well, it's kind of hard to do it this way. Can I do it some other way? You could. You can just count a success in this case as something that fills a category. So for instance, when it comes to this die, what do you have? You have 6 numbers. 1, 2, 3, 4, 5, and 6, correct? The question is asking you, what's the probability that you get a 4 or an even number? So you just go through the list and you just highlight the number that fits that category. So you highlight the 4, and then you highlight the even number, but you don't count anything more than 1. So 2 is an even number, 4 is already highlighted, so you skip it, and then 6 is not highlighted, so it's another success. And then from there, you can just go ahead and write your answer immediately. And that could make it easier for you. So instead of writing the rule of probability where you add and then subtract the overlap, you can just go ahead and identify what fits the description, right? You can do it with any one of those. Like here, highlight all the numbers that are 1 or even. So you can highlight 2, 4, 6, but you then also highlight a 1 because that's defined as a success. So the answer would be 4 out of 6, just 2/3. See what I'm saying? All right, here's another question of a classical probability. So we're looking at a deck of cards, and I decided to put the deck of cards right here. Okay, for those of you who might not be familiar with the playing cards, there are 4 different suits. All right, so this is called a suit. This right here, this right here, this right here, this right here. This is a suit. And there are face cards. These are the face cards. Okay, there's an ace. And there's the number cards from here to here. So they go from 2 to 10. All right. So, and there are 4 different suits. And within each suit, you have 13 cards. 13 times 4 suits gives us a standard deck of 52 cards. So that's the subdivision. 3 face cards within each suit, 1 ace, and the number cards is going to be 9. So from 2 to 10. Okay? Alrighty, so having that picture here in mind, we can go ahead and answer some of the questions right there. So this is an OR probability. So we're going to select a card at random from a deck, and you want to identify or find a probability that the card is a heart or a diamond. So by looking at this, okay, a heart and it says heart or diamond, right? So heart or diamond. And if you need a picture, it's right here. Okay, so these are the hearts, and here are the diamonds. And probability would be if you select any one of those cards that define a success. You can see visually this is exactly half of the deck. You can also see it by looking at hearts and diamonds and just adding them together, 13 and 13, which is 26, and put it out of 52. But notice that hearts and diamonds are what we call disjoint events. They do not overlap. A card can be a heart and diamond at the same time. So what do? We can write 1/2 right away, or you can go ahead and just say, okay, you have 13 of those. You have 13 of those out of 52, which gives us 26 out of 52, and that gives us 1/2. So you're adding those together. All right, I'll give you a moment to calculate the probability that the card is a heart or a king. A heart or a king. All right, let me give you a moment to write down your answer. A heart or king? Heart or king? Well, if you look at this, there are 13 hearts, right? Right here, there are 13 hearts. That's a success, correct? That's what defines a success in this probability calculation. And then you also have 4 kings. That's also a success. So if you add all the successes, how many you got? Well, you might say it's 13 hearts and 4 kings, which will give you 17. But that would be incorrect. Why? Well, because we're counting king of hearts twice. We count them as part of the hearts, and we also count it as part of the kings. But that would be incorrect because you're counting the same card twice. So one way to address this is to just go ahead and visually count. So we have 13 here, and then 14, 15, this we already counted, and then 16. You see, you're not double counting the cards. So that would be 16 out of 52. So that's one way you could do this, and we'll reduce it in a moment. Okay, so you can say it like that. There are 16 out of 52 that fits the description, which would be, if you divide it by 4, that would be 4 out of 13. You divide by 4, numerator and denominator. The other way you can calculate this is by using this addition rule of probability. How many hearts we got, plus how many kings we got, minus probability that you select both the heart and a king at the same time. So how many hearts? 13. How many kings? 4. How many cards are there that fits both description, a heart and a king? There's one card like that. And denominator is the same. So if you add the numerator, so that's going to be 17 minus 1. That gives you the same answer. All right, let's try another one. Part C, that we have the card is a face or 7. Face or 7. Face means jack, queen, or king, and a 7 is a 7. So in this case, you kind of write the same thing like that, or you can look at the deck of cards and count. All right, but I think it's logical here is to either write it like this or not. I think it makes sense that we have how many face cards? So we have 12 face cards. There are 3 in each suit. All right, so 3, 3, 3, 3. 3 times 4, 12. We have how many 7s? There are 4 7s. And can a card be a face and a 7 at the same time? No. So that's why we say that these two are disjoint. So you add them together, you get 16 out of 52. Again, by the way, which gives us the answer of 4 out of 13 as the final answer. Okay, so that's how we're counting. Alrighty, guys, we have one last question to do. Remember contingency tables that we did in chapter 1? So they're coming back at us again, but now we look at this from a point of probability of selecting somebody in that chart. But that would be very similar to the way we did the percentage calculation in chapter 1. So it shouldn't be very new. So let's look at the question. A political campaign conducted a survey of 4,500 local voters' opinions on some political issues. The following table tallies the result of the survey. So once again, we got some political affiliation, and we have some issues right there that are important. It says the candidate believes that being a Democrat and having a strong stand on the environment will be enough to get the majority of voters, but her campaign manager insists that she needs to also speak out on child abuse, who is right. So first, let's go ahead and be clear when we say majority. Majority in a political discourse means more than 50%. So let's define the majority. So more than 50%. That's what means majority of votes. That's called a pure majority. All right. So the candidate believes that if they target their campaign to just Democrats and also focus on those who talk about environment, then they should win that election. Not to win, but they're going to get majority, more than 50%. So from the probability standpoint, what's the probability of selecting that somebody who is Democrat or care about environment or important issues, the environment? So notice today's class, we're kind of focusing on or as being our dominant probability, or. So that is language that's important. So we say or. So success defined either being here, in this case, a Democrat, or addressed environment. So as long as you fit that categories, even if you're Republican, the voter is Republican, but cares about the environment, then this candidate that talks about the environment would be appealing to them. You understand? So this issue of or, and how do you read it from this table? We've seen those tables before. Okay, so in order for us to understand this, there are two ways we can do this. We can go ahead and look at this table and just highlight people who are either Democrats or care, the most important issues would be the environment. So can you go ahead and add all those candidates, not candidates, all these people in the table that either fell under the Democrat category or the one for whom the most important issue is the environment? I'll give you a moment. Well, if we check this, these are the Democrats, and these are the ones that care about the environment. Notice I didn't do the totals. I just did the numbers within the table because, these are the people who actually participated. The other ones are all the total. So the total is 4,500. All right, so if we look at that, all right, and if we just add these numbers together, the ones I highlighted, then we get an answer to the question immediately. So we got 430 plus 180 plus 440 plus 320. So that's 1370, of course, right? Because that's the sum of all the Democrats. And then you add these additional ones that are not Democrats, but most important issue is environment. So we're going to add 255 and we add 250. All right, so we add all these highlighted numbers, and that will be equal to 1875. And now let's see if that's a majority. So we're going to divide it by 4,500. And that gives us 41.7% about. And this is not a majority. Okay, so that's one way you can calculate. I think this is the easiest way, if you just highlight the parts that you got. The other way is to do the addition rule, is that you can go ahead and look at the Democrats. Then you add the one that care about the environment. And then you subtract the overlap. So it's Democrat and environment. And then what do we get? So how many Democrats we got? We got 1370 Democrats out of 4,500. So it's that sum. You see that one right here? Then you got the environment people right here, 945. also out of 4,500. And then you need to look at those that both Democrat and most important issues environment. So that you see this is overlap, you got to subtract it because that's going to count twice. And if you do this, you also get 1875, which also gives you 42%, 41.7. So less, it becomes less than 50. All right, so now looking at the campaign manager, she's saying that you also have to speak out about child abuse. So if you look at this again, and you add, in addition to Democrat and environment, if you add these voters for whom the most important issue is child abuse, then you get another 180, you see, right here, and another 440, those two numbers. So that's going to add it on to the tally. So that will give us what? We got percentage that it's a Democrat plus, or environment, or those for whom child abuse is the most important issue. All right, so you got 1, 2, 3. So looking at all of these, if you highlight all of those numbers and you add, we already added 1875 from before, and now we're going to add additionally 440 and 180. It's basically all the highlighted ones. And then you divide it by 4,500. Now let's see if we get the majority. So you got 1875, you add 140 plus 180, so that gives us 2195. And as you can see, that I believe is going to be more than a half. I think I rushed a little bit, right? I wrote 140 and it's 440. All right, so 440. So it's 1875 plus 440 plus 180 divided by 4,500. So that gives us 55.4%, and that's more than 50. So that is giving us the majority. This lesson was a little longer than usual, but what I want you to focus on is this concept of selecting probability or finding probability, and then you're talking about events connected to the word or, either this or that, as being a success. And when you do so, you need to identify, do you have an overlap or you don't? But the concept here is that you want to sum those chances together and subtract any possible overlap. And on that, we'll finish this lesson.